Hi, a little bit delayed, but here is the second part of the Arduino laser Morse code decoder tutorial. In the first part, we created the circuits for Morse code transmitter and receiver and figure out how to measure the length of laser signals and pauses in between them. With all this in place, we can finally do some Morse code transmissions. Maybe not as fancy as this one. It would look more like this. If you want to know if I succeeded, stick around. Working on this project, I really should say a few words about Morse code history, which is quite fascinating. Using Morse code, you can encode text characters as sequence of two different signals that have different durations, called dots and dashes. It is named after Samuel Morse, who invented this code in 1830. If his picture is not going to tell you how old this code is, I don't know what will. Amazing thing is that this code is still used by US Navy intelligence specialists, amateur radio operators, etc. Sure, it's not widely used, but still, just the fact that something invented in 1830 in the field of data transfer is used today blows my mind. The assignment of signal sequences to text characters looks like this. One thing I didn't know about this code was how this assignment was created. I thought it was kind of random. When you look at it, there is no apparent pattern that would explain why certain signal compilation was assigned to a certain character. And then I came across this tree-shaped diagram. To encode selected character, you start at the top and you move down. At each node, you either go left or right. Going left is represented by dot and going right is represented by dash. All letters can be represented with 4 signals maximum. As you can see, digits require 5 signals. But let's say we wanted to represent larger number of more obscure characters. All you need to do is to add one more branch level to that tree, and that will give you the possibility to encode additional 64 characters after agreeing how those characters should be placed within that tree structure. Ingenious, isn't it? To be able to transfer and receive Morse code, you need to set some guidelines on how these transmissions should look like. As I said, we have two possible signals, a dot and a dash. First, we need to decide what would be the length of the dot signal. It can be 100 milliseconds, half a second. It is a matter of convention. Whatever we choose, let's call it a unit. Then the dash signal would be 3 units. Apart from signal lengths, just as we discussed in the first part of this video, the lengths of pauses in between signals are also very important. So if the pause length is 1 unit, that means that incoming signal is the part of the same transmitted character. If that pause is 3 units, that indicates that we finished transmitting character and next signal will be the beginning of the next character in sequence. If that pause is 5 units, that means that we transmitted the last character of the word and next incoming signal will be the first signal of the first character in the next word in sequence. I think in some standards this should be actually 7 units, but I will stick to the smaller value. If the pause is greater than 8 units, that indicates that the transmission has ended. As an example, let's look at the character combination which is pretty much associated with Morse code. SOS distress signal. Let's encode it and play the transmission. You can see the dot's length is 1 unit. We also see 1 unit space between parts of the same letter. The space between the letters is 3 units. The dash length is 3 units. The transmission is finished with a pause longer than 8 units. So last week we created a building block of the Morse code project which consisted of interrupt service routines to detect and measure signals and pauses in between them. We need few more building blocks to complete this project. The next one will be to code Morse code representation and create a function which, when provided the sequence of signals, would identify which character that sequence represents. In the video that was showing how to create Morse code transmitter, I used this table to represent Morse code mapping. I guess this representation was okay for transmission, but I didn't particularly like it that much for the receiver part of this project. I decided to do it differently. I decided to create the structure that would hold a mapping for a single character. This structure would consist of character ID and string representation of Morse code signals associated with that character. Then I used this structure to create a table of Morse code objects. This table now is much more transparent and easy to read. Let's write a simple code to show the process of taking the captured Morse code signal sequence and checking it against the mapping table and finding which character is represented by that sequence. We define the variable that would store the captured sequence of signals. In setup, let's open the serial monitor. In loop, we mimic the process of populating RCVD variable one character at a time, just like we would by recognizing one laser signal at a time. So the sequence would be dot dash dash dot. Let's output that information into the serial monitor. Now we loop through the mapping table. In each iteration we display character, its corresponding Morse code sequence, and then we check if that sequence is equal to the sequence we populated in RCVD variable. If it is, we output the information that we found the matching sequence, otherwise we output no match string. Let's run this sketch. Here is our sample sequence. Here's the line of code that populated RCVD variable, and here's the result in the serial monitor. We scan through the table until the match is found. As you can see, we identify the sequence as letter P. Then the scan continues but finds no more matches. Let's do one more. Now the sequence is dot 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 dot. We have to update this line of code and run the sketch again. You see the table being scanned again, and this time letter H is identified. Obviously, in our final project, all we need is just a function without the serial monitor interaction. So we provide the captured sequence as an input, and then function outputs a character that is matched to the input sequence. So as an example, if we were receiving letter J, we would receive the sequence of 1 dot and 3 dashes. I would pass it to match letter function, which would recognize that this is a letter J, which can be then concatenated to the variable that would store the whole received message. Now we can have a look at the next building block of our project, which would translate the incoming laser signals into the string of dots and dashes that can be then mapped to the characters, which then can be joined into messages. This building block would heavily rely on the two building blocks we created previously. To start us off, let's look at the variables that we would need. This variable defines the pin to which laser sensor is connected. We will also need RCVD variable to capture incoming laser signals. Message would capture the entire transmission already encoded into text. Toll stands for tolerance. These signals will never have exactly the same length. They will differ by few milliseconds, and this tolerance parameter allows us to take this into account. 10 stands for 10% accuracy when measuring signal's length. Then we have the parameter that defines the length of the dot signal. All other transmission parameters are derived from this one, as we explained before. I start with it being half a second. When I get a working solution, we'll see by how much we can scale it down. I am hoping for 50 milliseconds, but we'll see. We have one more Boolean variable which indicates that the transmission has started and is in progress. Then we have variables linked to the building block we explained in the first part of this video. If you have not watched it yet, probably a good idea to do so now. So we have variables used to capture the length of signals and pauses in between them. Then also definition of interrupt in setup function and the interrupt service routine associated with it. Few minor changes here. If the transmission in progress flag is set to false, with the first signal received we set it to true, indicating that the transmission has started. Then I'm also adding the mechanism similar to the bouncing push button, basically ignoring all signal changes that are shorter than 10 milliseconds, treating them as glitches. Then we have parts of the second building block we discussed. The structure defining the Morse code object and the table containing the whole alphabet Morse code mappings. And finally, the match letter function. So now for the third block. In the loop function, if the transmission is in progress, we check if the interrupt service routine detected incoming laser signal. It is detected if the signal length variable is greater than 0. In this case, we check if the detected signal length is equal within tolerance to 1 unit. In this case, we add dot symbol to RCVD string. In the same way, if the signal length is equal within tolerance to 3 units, we add dash symbol to RCVD. After processing the signal, we reset the signal length back to 0, so it is ready for the next incoming signal. Then we also check if the pause was detected. It is detected if pause length variable is greater than 0. In this case, we only have to react when the detected pause length is equal within tolerance to 3 units. This indicates that the transmission for the single letter is completed, and we can try to identify it and add it to the message string. We output in the serial monitor the letter that was identified, together with corresponding dot and dash sequence. Then we reset the RCVD variable so it can record next incoming dots and dashes belonging to the next character in sequence. After processing the pause, we reset pause length back to 0 so it can react to the next incoming pause. This will allow us to capture all dots and dashes except the last one. Here we check how much time has passed since the last signal has ended, and if we exceed 8 seconds, that means that the transmission has ended. In this case, we perform the same actions as we would after detecting 3-unit long pause, plus we output the whole message as the transmission is complete now, and also set the transfer in progress flag to false, and reset the message variable. If after a while a new signal is detected, the whole process starts anew. To test this code, I have stripped the code from the Morse code transmitter video from text input functionality. Here I implicitly provide the text to transfer. I use the original Morse code character mapping. I have functions, one to extract the signal sequence for each transferred character, and the other one for sending laser signals for dots and dashes. In loop, I take the message to transfer, process it character at a time, using two mentioned functions to translate each character into laser Morse code signals. It's time to connect all required parts for this stage of our project. Let's start with the transmitter. So we need Arduino Nano and laser transmitter module. Minus pin is connected to Arduino ground, and signal pin can be connected to any input pin of Arduino. Here we connect it to digital pin 2. You just need to remember to adjust the transmitter code to reflect that connection. Now onto the receiver. Here also we need Arduino Nano, then laser receiver module connected to interrupt enabled digital pin 2. Both transmission sketches are loaded to corresponding microcontrollers, and it is time to run the first test. We will be transmitting text Arduino with the unit length set to half a second. First letter correctly recognized as A, 1 dot and 1 dash. Sketch carries on recognizing follow-up signals. The last one is missing, but let's wait 8 seconds. And there it is. Unfortunately, quite a number of times the transmission has failed, so I had cases of sequence being read incorrectly and thus wrong characters were recognized, like in this example, or messed up sequence did not match any character. In this case, the premature end of transmission was detected and the remainder of the text was treated like the whole new message. I contributed those failures to weak laser signal, and this was probably caused by this resistor on the main board of the module. I decided to test this standalone laser module that does not have that resistor. I printed the holder for it and will use the screw terminal to connect it to the breadboard. But before I replace it, let's do a quick test. Here you do not see it, but if I do a close-up, you clearly see the signal from the standalone module being much stronger. So let's swap the modules in our transmitter prototype. And here you have it. Okay, so with the new improved transmitter, let's do some Morse code transmitting. Here's the new setup. The transmission is going to be across my dining table, and also with longer distance, calibrating transmitter with the receiver becomes tricky. Let's do something more difficult this time. Let's transfer the whole alphabet and make a unit smaller. What the heck, let's go all the way down to 50 milliseconds. And the distance would be roughly 2 meters. Off it goes. Completed. No errors. Mind I say that transferring the whole alphabet in under 20 seconds is actually quite impressive. Most of the transfers I attempted completed successfully. So now to the last building block, which includes functionality to input text you want to transfer and also display the received message on the other end. For both, I would use OLED displays. I'm not going to show you this part of the project in detail because the code is just way too complex, and also with OLEDs I ran into the memory problem on a receiver part of the project. Basically, OLED display allocates 1K of RAM to buffer its activity, and together with the memory needed by my sketch, the measly 2 kilobytes of RAM provided by Arduino Nano got exhausted. I managed to fix it. The whole ordeal actually calls for entirely separate video. I just need to find time to make it. Starting with the transmitter, we are adding the I2C OLED display connected to I2C pins A4 and A5, and then also 5-key keyboard module connected to one of the analog pins. On the receiver part, we just add the OLED display, also connected to pins A4 and A5. Time to take this prototype for a spin. Let's power on transmitter and add the text we want to transmit. Now that it is ready, I calibrated both modules, and let's press the button to start the transfer. It works, and it looks quite cool too. It's time to take it outside and run some longer distance tests. I quickly realize I made a mistake powering laser module from Arduino. Arduino cannot provide enough current to get the maximum brightness, so here are the changes I had to do to power it from 5-volt external power supply and use MOSFET transistor to control its on and off state. If this is new to you, I suggest you watch one of my videos where this topic is covered in detail. So here is our transmitter circuit. I added external power supply and a transistor. Transistor has 3 legs: gate, drain and source. We connect laser plus to positive side of the power supply. Then minus goes to drain. Source goes to ground. Arduino D2 pin goes to gate. Gate is also connected to ground via 10K resistor. Grounds of both Arduino circuit and laser circuit need to be connected. We can even power the Arduino from an external power supply. Now, when I start any transmission, you see that it is super bright. That will definitely improve the success ratio of the transfers. So let's take this improved prototype outside and test longer distances. And I have to say that that was a slight disappointment. It was difficult not due to technical problems. Calibrating the both transmitter and receiver was super difficult. Here is the transmission over 5 meters, and you see that the first character is misspelled because pressing the button to start the transfer is causing micro movement which affects the transmission. I wanted to do more tests, but it was getting dark and mosquitoes were eating me alive. At the end of the day, even though it was a minor setback, I had a lot of fun working on this project, and I rate it as a win. This concludes this video. I can cross another item from my project bucket list. Like and share this video. Subscribe to my channel if you like this type of content. Please consider supporting me either through PayPal or Patreon. Actually, right now you can support my channel directly in YouTube. If you go to my channel page, you will find a join button. By pressing it, you're joining Mario's Ideas community with all the bonus stuff that comes with it, supporting my channel in the process. I will see you in my next video. Ciao!